All right, so let's take a look at where the water and the atmosphere comes from, because those two things are definitely linked just like they are today. So if we take a look at our early atmosphere, odds are our early atmosphere derives from the impacts of comets and meteorites, right? So all the material that's essentially being blown off from these impacts is getting pulled in by gravity to essentially circle around the Earth, right? So our early atmosphere is probably derived from this material. If we take a look at Halley's Comet, which is a very well-studied comet that rotates around Earth in a very large orbit, it's made up of just 80% old water ice, okay? It also has some carbon dioxide ice, and we do find some other interesting things, right? Like our good old friends, iron, magnesium, oxygen, and silica. Then these things shouldn't be odd either. We also see that we can find both on comets and some of our meteorites. Remember that organic material, okay? So those carbonaceous chondrites, that's pretty important. So as we're getting these impacts, right, materials getting blown off, and it's starting to make our early atmosphere. But don't think that's what's really creating our water, because that's not a major process there. What's really starting to create our water actually ties right back to plate tectonics. So remember, as we have subduction, let's review that again. As we have subduction, we're generating magma, right? That magma is going to come up and out of a volcano. So we have a lot of volcanoes that are erupting at this time in early Earth. There's a lot of komatiite plates, and there's going to be a lot of collisions. Plates are moving a lot faster than they do today. So we've got a lot of volcanoes going off. So when a volcano erupts, what comes out, right? Well, we know we obviously have liquid rock, right, that comes out. That's lava. But we also have a lot of gases that come out as well. We call that outgassing, right? It's the gases that come out. Now, if we study today's volcanoes, which Kilauea is by far the most well-studied volcano on our planet. It's been erupting every day since 1983. If we take a look at it, what we see is most of what comes out of there is just water vapor. Nothing special, just good old steam. Well, if we have a whole bunch of these volcanoes that are going off, and a lot of them are giving off steam, we're going to start to collect a lot of water vapor in the atmosphere. And we live in southeastern Louisiana, so we know this. What happens when a lot of water vapor collects in the atmosphere? Right, it rains, right? So, quite literally, the oceans came from rain, okay? From outgassing from these volcanoes. So that would be the start of the hydrologic cycle. Now, I don't want you to think that it happened really fast, right? You didn't go to bed one night and wake up the next morning and poof, you've got oceanfront property. This probably took over 2 billion years, okay, for the oceans to get anywhere close to where they are today. However, we do have to realize that if the oceans essentially started out, right, as rainwater, that means that they were fresh water, okay? Obviously, today, the ocean is pretty salty. So over time, right, the ocean is going to have a higher salinity. Today, it's a pretty constant salinity, and we're going to talk more about how that change happens as we go through the semester. But you can always think back to Geology 101 and think about how salt gets into the system. All right. So we've seen plate tectonics, we've seen water, we've seen the atmosphere, but there's one key thing we still haven't talked about yet, and that's our good old friend, oxygen. And oxygen is important because it's keeping us alive. In Earth's early atmosphere, there was no oxygen. And we know this because of the presence of these guys. These are banded iron formations, or BIFs for short. And what's really interesting about these is essentially how they form. We think that banded iron formations essentially form at the bottom of an ocean around hydrothermal vents or volcanic vents. And essentially what's happening is, remember, early early crust was komatiite rich, right? Which means there was a lot of iron. So as water is eroding across that komatiite crust, it's delivering a lot of iron out to the oceans. So in the oceans, let's draw a little ocean here. In the ocean, we've got a lot of iron molecules, right? Or iron atoms that are essentially floating around in there, right, as sediment. We have these volcanic vents, okay, that are sitting at the bottom. And those volcanic vents are releasing gases out into the water. So, of course, oxygen is going to get released out into the water, free oxygen, right? O2. That oxygen, of course, is going to bind with the iron. So what happens is we see these huge points in time where we're releasing a bunch of oxygen into the oceans. That oxygen is going to combine with the iron, and essentially it's going to rain down as a layer of rust, right, on the ocean floor. And then, of course, the whole process is going to start over and over again. So if you take a look at a banded iron formation, you see, right, these layers of red in here, right? That's those layers of rust that are raining down onto the ocean floor. So quite literally what we're seeing here is the Earth breathing, right, taking those first breaths. And, of course, oxygen is not going to get out into the atmosphere until we've burned through, essentially, all of that iron in the ocean. And then the oxygen, once it builds up in the water, can then bubble out, essentially, right, into the atmosphere. So what's pretty cool about this is we think about first life. So that means first life on our planet developed where there was no oxygen, meaning it was anaerobic. Okay? Sounds kind of crazy, but we actually have bacteria today that's definitely anaerobic. Botulism, if you've ever been unfortunate enough to get that, doesn't need oxygen, so it is anaerobic. So what's interesting, again, is, you think about how life developed on our planet and we take oxygen for granted, but realize that oxygen wasn't always there. It's not a necessary requirement for life, especially for early life. But how does oxygen get into the atmosphere today? Well, there's two processes, one major, one minor process. I would hope the major process is obvious, and that's photosynthesis, right? Our good old green plant friends, right, making lots of oxygen for us. The other process is called photochemical dissociation, where essentially we have water molecules that are high up in the atmosphere, and when the sun's rays hit that water molecule, remember that's H2O, right, the oxygen gets really excited and the hydrogen gets really excited, and essentially this molecule breaks apart. So you end up with free oxygen in the atmosphere. Now this is a minor process, okay? So again, don't think that this is where all the oxygen comes from. This is a small part of that. So when do we start seeing a lot of oxygen in the atmosphere? Well, we have two things that we can find on our planet that give us clues. The first thing would be red beds. Remember, anytime you see the color red, that means it's oxidized iron. So when I start to see lots of oxidized iron, that's definitely telling me there's oxygen in the atmosphere. The other thing is carbonate rocks, like limestone. We need oxygen in the atmosphere to form our carbonate rocks. Carbonate rocks definitely tell us that we've got photosynthesis going on, that there's less carbon dioxide in the atmosphere, which means that the water is not as acidic. And when the water is not as acidic, then those carbonates can develop. Carbonates dissolve in acidic water, which is essentially how we form caves. Which, interestingly enough, we see both red beds and carbonate rocks appearing in the rock record 1.8 billion years ago. So this tells us about 1.8 billion years ago we have enough free oxygen in the atmosphere that the Earth definitely changed.